Recently, devices like haptic suits are becoming more common in the market, and they're taking the immersion of VR games to the next level. However, there's a catch. The haptic feedback for these suits has to be manually crafted by experts for each piece of content, which means it's hard to make full use of these suits. To solve this, we propose a semantic sound-to-haptic conversion system. This system analyzes sounds in real time, figures out what's happening in the game, and then provides the player with appropriate full-body vibrations. For this, we use a haptic suit equipped with voice coil actuators, along with forearm straps and VR controllers. Here's a demo of our system. There are three main components to our semantic sound-to-haptic conversion system. First, the classification module captures the sound stream using a sliding window technique and classifies what the sound means. Based on this, the haptic pattern module pulls up pre-designed vibration patterns tailored to specific events. Finally, the haptic rendering module combines the processed sound signal with the intensity patterns to create actual haptic signals, which are then distributed to each actuator. Most of the processing happens on the PC, but the part where the sound signal is combined with the intensity pattern and distributed is handled by an external audio processor board. Now, let's dive into each module. The classification module captures 50 milliseconds windows of audio every 17 milliseconds, matching the frame rate of 60 frame per second videos. The captured stereo sound signal is transformed into magnitude spectra using a Hanning window and FFT, then concatenated to form an input vector. We implemented an LSTM classifier to calculate scores for each sound class. To do this, we created our own dataset by labeling frames that contained our target sound classes. In this study, we focused on FPS games and chose gunfire, being hit, nearby explosions, and reloading as our target sound classes. To improve the classifier's robustness, we applied time-shifting augmentation and left-right mirroring, increasing the dataset by 22 times. However, relying solely on the scores from the LSTM classifier might not be enough to precisely detect when sound events start. So, we set threshold values for each class. As shown here, if a gunshot occurs, but the classification results are consecutive, it might mistakenly recognize multiple events. To fix this, we introduced a timer that assumes the same classification result over a set period is from one single event. But there's more. What if another event happens while the score is above the threshold? To catch this, if there's a sudden change in the score beyond a certain value, we count it as a new event. Now let's move on to the haptic pattern module, which generates vibration intensity patterns based on the classification results. To design these patterns, we interviewed people to understand the expected tactile sensations for each class. Some sensations, like the recoil from shooting a gun or the feeling of being penetrated when hit, are hard to replicate with just static vibrations. So we used a technique called phantom sensation, which is a tactile illusion. By gradually changing the intensity of stimulation between two actuators, it creates a sensation as if the stimulation is moving or penetrating through the body. Using this, we designed specific intensity patterns for each class. For example, shooting or reloading creates a sensation moving from the controller to the forearm band, while being hit creates a sensation that feels like it's penetrating from the chest to the back. For explosions and other events, we designed the vibration to be felt across the entire body. You can see examples of these patterns in this video. Now we need to generate the actual haptic signals and distribute them to each actuator. To convert the sound signals to haptic signals, we first applied an octave shift and a low-pass filter. Then we multiplied these signals with the intensity patterns generated by the pattern module, creating the signals applied to each actuator. This whole process, from start to finish, takes less than 60 milliseconds, making it feel almost real-time. To evaluate our system, we conducted a user study comparing 3 different ways of providing haptic feedback. The first was non-semantic, providing vibrations across the whole body regardless of context. The second was semantic, but with randomly assigned haptic patterns. And the third was our method. Note that we weren't focused on gameplay, but rather watching gameplay video, since the actual gameplay caused severe motion sickness. The results showed that our method significantly outperformed the others in various aspects of user experience. Our research shows that even games without pre-authored haptic effects can still offer an immersive experience. For more details, please check out our paper.